So today we want to look at the 18 electron rule. I said we want to look at the 18 electron rule. So we all know that in the valence shell of transitional metals, they have 9 orbitals, and those 9 orbitals must accommodate a maximum of 18 electrons. So if it has 18 electrons, it's said to be stable. So even metal complexes, if a metal complex has 18 electrons, it is said to be stable. So today we want to look at how can we use the 18 electron rule to predict the stability and the structure of organometallic complexes. But our focus is to look at metal carbonyl complexes, a metal which has been bonded to carbon monoxide. That's what we are going to look at today. That's what we are going to use to demonstrate the 18 electron rule. We are going to do the electron counting, but using the neutral method. If you look at a metal, if you have a metal which has been bonded to carbon monoxide, each carbon will be able to donate a pair of electrons towards this metal. So each carbon in the carbon monoxide donate a pair of electrons towards the metal. Now, we have quite a number of metal complexes that we are going to use today. The first of that kind is this complex of chromium, which has been bonded to 6 carbon monoxide. So let's do the electron counting. We said chromium in 0 oxidation state, it's a D6. Remember, chromium is a first row transitional metal element. It's a D6 and it has 6 electrons. It's surrounded by 6 carbon monoxide, but each one, we have said each carbon should be able to donate 2 electrons towards the metal. So these are 6, giving us a total of 12 electrons. So the overall total is 18 electrons. So this complex is said to be more stable. So because it obeys the 18 electron rule. Our second example here, it's a complex of manganese. It has a metal to metal bonding. It has a manganese to manganese bond. So if you look at this Mn2CO10, each Mn is surrounded by 5 COs. Each Mn is surrounded by 5 COs. Doing the counting, neutral counting, Mn, 0 oxidation state, it's a D7 from the periodic table, and therefore it has 7 electrons. It's surrounded by 5 COs, each one contributing 2. It gives us a total of 10 electrons. It also has metal to metal bond. Metal to metal bond contributes 1 electron. So the total is 18 electrons. Therefore, this complex is stable. Then our third example is the one of MnCO5 minus. It's a charged species. It's still Mn, 0 oxidation state. It's a D7, 7 electrons. It has 5 COs. Those are 10 electrons. It also has a negative charge. A negative charge contributes 1 electron. So giving us a total of 18 electrons. So therefore this complex is very stable. Then the fourth complex, it involves a bridging carbonyl. It involves carbon monoxide that links up 2 metals together. So this complex has 2 types of carbonyl. It has a bridging one, and it also has a terminal carbon monoxide. So iron, 0 oxidation state, D8, 8 electrons. 3 carbon monoxide are terminal. 3 are terminal, 6 electrons. Then it has a metal to metal bond. Metal to metal bond, 1 electron. It has bridging carbonyl. Bridging carbonyl, they are 3, each one contributing 1 electron. So this is 3 electrons giving us 18 electrons. So this complex is said to be stable. Then our next example is this complex of vanadium, VCO6. So V, 0 oxidation state, D5, 5 electrons, 6 COs, 12 electrons, giving us a total of 17 electrons. This one does not obey the 18 electron rule, and therefore it is unstable. Then our last complex, it involved a metal cluster. It has more than 2 metals. This is ruthenium. These are 3 RR. There are 3 of them. So there are 3 of them, but when you're doing the counting, consider only 1 metal. So each metal is surrounded by 4 carbonyls. So 4 carbonyls, 8 electrons. Ru is a D8 second row, that is 8 electrons, and each Ru is joined up to 2 others. So these are 2 metal-to-metal bonds, 2 electrons, giving us 18 electrons. Therefore, the complex is said to be stable. So for today, that's what I wanted to look at. Remember to always subscribe to my YouTube channel.